to my master, which I finished 2 years ago in the University of Kansas. So that. I will be talking about the development of a highly stable lamella using polyelectrolyte complex nanoparticles. This method is an environmentally friendly supercritical CO2 foam injection. The main purpose is providing the energy for the world energy consumption and simultaneously focus on the greenhouse gas management. Why are we interested in this area? So based on the report from EIA in 2017, we expected the world energy consumption, we expected that the non-fossil fuels kind of provide the world energy consumption, but in the same report, we see that the fossil fuels are still counting for more than 3/4 of the energy consumption. So we are interested in that. But we are looking for the method that make it more environmentally friendly. In the same time, we are producing 35 billion tons of CO2 annually, which is huge and significant, and we need to take care of that because of the huge challenge that we are dealing, which is related to the greenhouse gas control. So what we can do in the oil and gas industry, our solution is we can come up with the methods that we can utilize the carbon capture and sequestration during the oil and gas recovery processes. So we are interested in the CO2-EOR. The CO2-EOR methods actually accounts for 6% oil production in the US. These days, and we produce 62 million metric tons of CO2 due to the EOR processes in the US, and the CO2 sources coming from the natural gas processing plants and other sources. Why are we interested in the CO2 flooding, CO2 foam flooding? Because the gas injection was used as a good technique to improve the oil and gas recovery from the reservoirs, but there are multiple problems associated to the gas injection. When we inject gas, our gas has a lower density and viscosity compared to the fluids in the reservoirs. Therefore, because this one is lighter, the gas that we are injecting, it will bypass the reservoir and it will go to the production wells, and we end up with a lot of the reservoirs being unswept, and the recovery efficiency will go down significantly. We inject foam because foam actually improves the viscosity and the density of the injected gas, and therefore it provides us the good mobility control for the gas that we are injecting. And basically, this method is known as a proven techniques for the CO2 storage and sequestration. Based on some of the literatures, which mainly was done by Clay Radke in 1980s, during the gas injection processes, and especially when we are going toward the foam injection, we normally trap between 40 to 80% of the gas in the reservoirs, which means that we are producing energy, and in the same time, we are trapping the CO2 under the ground, which helps us with controlling the global warming. And also, the CO2 that we are injecting in the hot reservoirs and in the high salinity environments, it doesn't show a good result. Therefore, we are interested in these techniques. What is foam? I don't know how many of you heard about foam, but foam is considered as a special colloidal dispersion. It consists of a gas, a liquid, and a foaming agent. Basically, the foam quality is the most important property of the foam. The foam quality defined as the ratio of the injected gas to the ratio of the total injected fluid. And we are interested in the very high quality foams in the oil and gas industry. The oil field qualities that we are using are in the range of 75 to 90%. As we move toward the hydraulic fracturing job, we go to like drier foam, which is getting close to the 100%. And also, with the foam, we have the ability to control the unwanted gravity override problem that is associated with the gas injection. We use surfactant. As I mentioned, surfactant is the foaming agent that we use. Surfactants are, as we know, are the materials that are used to change the surface tension. Basically, we are interested to decrease the interfacial tension because there is a big tension between the oil in the reservoirs and the rock in the rocks that we have the oil wet and water wet reservoirs, but mainly I'm talking about the oil wet reservoirs. So there is a big interaction between oil and rock, but we want to decrease that interaction, that attraction, so we can produce the oil as easy as possible. So for that purpose, we use surfactants. And about the CO2, so we have the opportunity to use CO2 in the gas phase or in the supercritical phase. In the gas phase, CO2 has a very low density and viscosity and results in the problems that I mentioned before. But in the supercritical state, which is in the temperature above like 30 degrees C and the pressures above around 1,000 psi, the CO2 density will increases significantly, and it becomes close to the water, to the liquid phase. So therefore, we are interested in this area to control the mobility problems in the recovery. Sorry. In this method, we are trying to use specific systems of the nanoparticles. Why do we do that? Injecting surfactant by itself, surfactant-generated foam, results in improving the recovery. But we have different problems when we are in the high salinity reservoirs or when the surfactant-generated foams actually interact with the oil in the reservoirs. The foam is thermodynamically unstable, and it will break as soon as it touches the oil in the reservoir. So we are looking for the methods to improve that stability of the foam. Therefore, we are using the nanoparticles. The nanoparticles, they improve the viscosity of the foam by charging the interface. I will explain it later when I'm talking about the mechanisms involved. The system that we are using is a branch PEI and the dextrose sulfate. The PEI is a polycation, and the dextrose sulfate is a polyanion. So the combination of them results in like a bonding. And both of these chemicals that we are using are water soluble, and both of them are biodegradable and biocompatible. I will talk about the effect of the nanoparticles later because I have a lot of slides. Another important aspect of this work is the produced water. So in the United States, as far as I know, we have 2.5 billion gallons of produced water like every day. So we need to take care of that. That's a big challenge for the industry. We have multiple options to take care of the produced water. One of the options is to dispose them, but we always hear about all the earthquakes and all the environmental agencies acting against oil and gas industry because they think all the earthquakes coming from the disposing the produced water. It can be true if it is not done very carefully and with a lot of studies. So that option is expensive and is dangerous. The next option is to treat the produced water and use it. But a lot of the water that we are producing from oil and gas reservoirs are having a very high concentration of the divalent ions, which sometimes is very, very expensive or even impossible to be removed from the water, and we can use it again. The third option is to re-inject that water into the reservoir for the further oil recovery processes. By looking at the map for the distribution of the wells and the produced water in the US, which is shown here, we can see that a lot of these are the wells that are now distributed in the US, and those are the produced water associated with it, basically the salinity of them. We see that a lot of the wells in the Midwest toward Texas area are in the high salinity range. High salinity range, which is, we call it dense brine. The total dissolved solid is in the range of 200 to 250,000 ppm, which is a huge number. Therefore, in this work, we are trying to develop our system in a high salinity produced water and inject it into the reservoirs. We know that the high salinity and the high temperature of the reservoirs and all of these problems associated to breaking the foam easily. Therefore, we use the nanoparticles to stabilize our system. So we have the PEI and DS, we generate the nanoparticles, and then we combine it with the surfactant solution, and this will be our aqueous phase, and we inject it with the supercritical CO2 into the reservoirs. And all of these are prepared in the Mississippian limestone brine, which is 200,000 ppm salinity. But our system, we did it in the 33,000 and 67,000, which is mainly due to the instability of the surfactant in the solution. Our nanoparticle solution is stable, even up to 200,000 ppm. But the limitation factor is the surfactant. So we use different materials and methods. We use TEM and Raman spectroscopy to visualize and investigate the nanostructure of the particles in the solution. We use the dynamic light scattering for measuring the size of the particle. We don't want to clog any of the pores in the porous media. And we use the Anton pyriometer to measure the viscosity and rheological properties of the solutions. We have a CMC measurement and the IFT measurement. We are interested in measuring the interfacial tension, and we are interested in CMC. Basically, CMC is the critical micelle concentration. CMC can be obtained by measuring the physiochemical properties of the surfactant versus the surfactant concentration. When we increase the surfactant concentration, the IFT decreases, and it reaches to a state that after that, any further increasing of the surfactant concentration will not change the IFT. We are interested in that point. That point is called the CMC. We want to stay below that point in order to prevent generating like the coagulation of the surfactant particles. And we have a core flooding system. Basically, we inject our developed system into the core that is saturated with the oil, and we look at the result and see how much we improve the oil recovery. All of this work has been done in 30-50 psi and 40 degrees C. And the foam quality is 90%, which means 9 part is the gas and 9 to 1 part is 9 part is the gas and 1 part is the aqueous phase. So we measure the size of the particles and the zeta potential. The size, we care about it. We don't want to clog any of the pores. And the zeta potential shows the charge on the surface of the nanoparticles. So we measure it for all for different samples in the 33 and 67,000 ppm. All the results that we have, it shows that adding the nanoparticle solution to the surfactant solution improves the zeta potential, which means it improves the stability. The same result for the 67,000. And then we looked at the TM. We kind of claimed that our nanoparticle system improves the stability of the surfactant solution. But how? We looked at the TM. The TM result is showing for the surfactant case, for the polyelectrolyte complex nanoparticle, and for the combination of them. As we see, the distribution and the direct absorption of the surfactant monomers on the nanoparticles is an indicator of the existence of the electrostatic forces. The electrostatic forces are counted for stabilizing the lamella. Therefore, the liquid cannot drain in the lamella, and the foam will stay stable. And then we go to the Raman spectroscopy. So we showed the spectrum for the surfactant case, PEI case, PEI nanoparticle case, and we showed it for the surfactant and nanoparticle case. Each of these peaks corresponds to a specific functional group. So we kind of measured this spectrum for the sample, which is a mixture of the surfactant and the nanoparticle. And we try to fit a model that is obtained by summing up the spectrum from each of those. basically, and the areas that we don't see that they coincide are the areas that we are interested in. Basically, those areas indicate the change in the chemical environment of the solution. We have two areas that we are interested in. The first one is here, and the next one is here. Based on the literature in the bioengineering, the shifting or intensification of these peaks corresponds to the existence of the electrostatic forces. So this one corresponds to the sulfate group, and this one corresponds to the interaction between aliphatic aromatic chains in the surfactant and the amine groups in the nanoparticle solution. So we can check the boxes that we literally, and we prove that our system improves the stability by the electrostatic forces. With that, we look at the dilatational elasticity. We want our interface to be stable and to be elastic. Basically, if any changes happens to the interface, we want it to be elastic, so the foam can get back to the previous station, because as soon as the foam breaks, it's useless, and we are not interested in it. So we want to keep it as much as we can. So we showed that by adding our nanoparticle system to the surfactant solution, we improve the elasticity of the surface significantly. And this is even higher for the higher salinities. And all of this shows that we are improving the disjoining pressure, and therefore we improve the stability. With that, we looked at the stability of the foam. We measured the foam decay time, and we showed that the nanoparticle system for the 33,000, the ratio of 1:9, and for the 67, the ratio of 2:8 shows the best result. We took that wanted to compare it with the surfactant solution, and it kind of approved and confirmed our previous results. With that, we take, I can go through this. We checked it with the oil, because we are interested in the oil, and in the reservoir we have oil. So we see that by adding the nanoparticles, we basically improve the stability of the interface, which is the most important part of our work. We don't want the foam to break as soon as it sees the oil. So this is very favorable for our application. And also, we improve the foam light for 100% or 200% for different salinities. So our system is ready to be injected into the core. But we looked at the rheological measurement, just wanted to show that we improved the viscosity. And it shows that by fitting a power law model to the viscosity versus shear rate measurements, we show that, yes, this system improves the flow consistency index, which can be translated to improve the viscosity. With that, we injected our system into the core that is saturated with the crude oil. So we have different scenarios. For the first case, we didn't have crude oil. We just wanted to look at the effective viscosity of the foam, and we found out that adding the nanoparticles improves the delta P, and this delta P corresponds to the effective viscosity. So here we are good. Now we inject everything into the core that is saturated with the crude oil. We use different cores and with different orders. So the core is saturated with oil. We did the water flooding, and then we did surfactant, nanoparticle surfactant, or polyelectrolyte surfactant system. In one of the cores that we injected surfactant after the water flooding, we saw like 45% improve after that. And then we didn't see any more oil coming out, and then we injected the nanoparticle system, and we saw that we increased 10% the oil recovery, which is huge, because sometimes even 2% is a great number for the oil and gas industry. And in the other case, when we started with the PCNP surfactant solution, actually we produced 54% of the oil in place after water flooding, and then by injecting the PI after that, we produce like 20% more. It means that the combination of these systems can be, this is kind of the order and the amount that we produce. The combination of this system can be used for the wells that are not touched after the water flooding. So we can start with the nanoparticle system, and we produce a lot of the oil, which the total production can sometimes go to up to the 80%, which is a huge number. And in other cases that had been already surfactant flooded, we can inject the nanoparticles and we produce 10% more of the oil that has been left in the reservoir. So with that, we used this technique to reduce the wastewater disposal and use it for our oil recovery processes instead of fresh water. And we also, this method is considered as a carbon storage and sequestration because as I mentioned, is the CO2 trapment is between 40 to 80%, minimum 40%, and in many cases it's close to 80%. And we showed that this system stabilizes our foam, and we increase the recovery, and we improve the oil production with that. And these are the list of our references, and these are the list of my acknowledgement. And thank you very much for your attention, and I would be happy to take any questions.
Fascinating work. So I don't quite understand the supercritical CO2 with water lamella. What does that mean? So why do you say it's a lamella?
No, supercritical CO2 is kind of close to the liquid phase.
It's a fluid, yeah, right. So, is it miscible with water?
It's miscible with the fluids in the reservoirs.
So you said the supercritical CO2 / water lamella. So do they mix together or not?
Well, basically, yes. Actually, the solubility of the CO2 is huge in the water, yeah.
And then you show the TEM where I guess in the TM, the vacuum, they have already left. Could you show that slide again?
This one?
Yes. So the nanoparticles and the surfactants. So I mean, all the fluids have gone, right?
Mm-hmm.
So
because it's vacuum? Well, actually, we used, it's kind of a porous media that we use, and our solution is kind of trapped between the two like copper grids, and then after that we apply the vacuum. So basically, the solution is still there.
It's trapped between the copper grids?
Yes.
And what's the scale bar here? Like the length scale?
I am not sure what is the scale bar here.
Very small.
Yeah, 500 nanometer.
So the nanoparticle size is very small, actually.
Yes, actually, we want everything to be smaller than like 100 nanometer, because the pore structure is in a way that it's very small and in the range of nanometer. And if our nanoparticle system is big, it's going to clog the pores, and we don't want that to happen. And in another situation, if the nanoparticles are very big, they will precipitate in the solution, and they will not help for our purposes. So we are sure that the sizes are small. We did a screening test because of the time limits. I didn't talk about it. We did a screening test on the size of the nanoparticles and the system that we want to use. So based on the size of the nanoparticles and the charge on the interface, we chose these systems to go with and to continue the rest of the experiments.
What's the air fraction in the foam? You said this is...
Yeah, this is 90% quality foam.
So we have 90% air? And
no, we have 90% supercritical CO2. Our system doesn't have air. It's supercritical CO2 and the aqueous solution, which is surfactant and nanoparticle.
And the water is on the CO2 side?
Water is on the aqueous phase. Basically, surfactant and nanoparticles are dissolved in the water, yeah, in the produced water.
I didn't quite understand the conclusion about the greenhouse gas management. Is the claim that you're going to be using less CO2 for the same amount or for more kind of output, or is it that more of the CO2 will stay in the ground? Can you just speak a little bit more about the evidence that you have for that?
Well, we have some data that we measured, but we didn't include it because we had a lot of slides. But by the system that we compared the CO2 that we produce for the surfactant CO2 injection cases and with the nanoparticle cases. The amount that we are producing, we measured that one, and we showed that it will help with the CO2 treatment as well.
And those measurements are done over a long